Alright, number 44. The star HD102272 has two planets. Planet A has a period of 127.5 days and a mean orbital radius of 0.651 astronomical units. Planet B has a period of 520 days and a mean orbital radius of 1.57 astronomical units. What is the mass of the star in units of the sun's mass? Alright, back what we was talking about yesterday, okay? You're right, we're going to do this formula. We got somebody that's turned the heat up. Alright, so the period is equal to 2 pi times square root of the radius, the distance from the planet to the star cubed, divided by the gravitational constant times the mass of the star. We're going to use this. Okay, we're not going to try to link them together. They gave you pieces of information you don't need. Just choose one of the planets. Y'all said that you want to go with planet A, so let's do planet A. Planet A. So planet A has a period of 127.5 days. A radius of 0.615 astronomical units. Alright, now in this question they are asking you the mass of the star in units of the sun's mass. Before we do anything with the sun's mass, let's find the mass of this star, and we're going to try to do it in kilograms. So, let's do it with the formula first. Let's try to get the formula by itself. I need mass of the star by itself. You're just going to square everything. I'm just going to jump. If you got a question, just ask. So, period squared equals 4 pi squared times radius cubed over gravitational constant times the mass of the star. I'm sorry. I cannot. Y'all are roasting me.
Roast session.
I didn't even feel any change there, honestly.
I'm dying.
I ain't saying, I don't.
Alright. So, does anybody got a question how I got to here? I just squared it. Everything's squared. Both sides got squared. Solve for the mass of the star by itself. So the mass of the star is equal to 4 pi squared times the radius cubed all over gravitational constant times the period squared. Alright, I'm going to stress this to you all. You all just keep jumping for units. You just keep grabbing units. And you're really not using your units. You best use your units. And you best know how you're getting the units that you're getting. So in this case, what is the gravitational constant units? It's newtons times meters squared over kilograms squared. What's a newton? What's the units break into?
Kilogram minus meters over s squared.
Kilogram times meters over second
Sure, I
squared.
got mine.
Positive.
Are you sure?
I'm positive.
I don't know about that.
I was just doing it.
There should not be a minus there. It should be multiplication. If you think about what's force equal to, force equals mass times acceleration. What's the SI unit for mass? Kilograms. Acceleration, what do we use acceleration? Meters per second squared. Meters per second squared. So you got mass, kilograms, times acceleration, meters per second squared equals kilograms times meters over second squared.
Yeah, I know that. It's like that.
Okay, this is the key, and this is why I'm getting ready to do what I'm about to do. This is in seconds.
We gotta change the period.
This is in days. I cannot use that.
Not yet.
I have to convert that. And I have to convert it to seconds. Why do I have to do it to seconds? Because this is in seconds. So, 127.5 days. I need days to get to hours. So it's 24 hours in a day, so times 24. I got hours. I need hours into minutes. There's 60 minutes in an hour, so times 60. I need seconds, so there's 60 seconds in a minute, so times 60 again will give me 11,016,000 seconds. That's the period of planet A. All right. And then there's this one. I need to convert astronomical units as well. We're not going to be able to use those. So we need to get it in units that we're used to. And this is the key. I'll even write it in purple. It's important. One astronomical unit is equal to the average distance of the Earth to the Sun. Which is equal to 1.50 times 10 to the 11th meters. That's coming off at table 1 out of your book. Also coming off of that I put over on the board for you all. All right. So in this case, I need to convert this. So let's convert it. So I have 0.615 astronomical units over 1 times, I need meters left on top. I need astronomical units gone, so they go on the bottom. So there's 1 astronomical unit, and how many meters are in an astronomical unit? 1.50 times 10 to the 11th. Answer your question. Will I put this information on your quiz on Friday? No. But you have that information because I'm giving you that. The only thing you have to remember is 1 astronomical unit is equal to the distance from the Earth to the Sun. That's it.
I have a question.
Yeah.
So not within, whenever this you want to throw at us, right? On quiz.
Yeah.
All is very good.
What you learn, don't forget it.
I won't forget it.
So, do this in a calculator. .225 times 10 to the 10 meters. Okay. There's my radius, and there's my period. Now I can really start using this. Now I can do some math, plug in things that I know. So I'm going to come back over here. Alright, so mass of the star is equal to 4 pi squared times the radius cubed. The radius we just solved for. There it is, 9.225 times 10 to the 10 meters cubed. Notice I'm carrying my units with it. That's divided by the gravitational constant, which you should memorize as 6.67 times 10 to the negative 11 newtons times meters squared all over kilograms squared. times my period squared, which is 11,016,000 seconds, and that's squared. So we're going to throw this in the calculator. Squared. Five. 10. Power. It's all divided by 6.67. 11. That's right. And this is what I get. 3.8 290 times 10 to the 30, and it's kilograms. How do I know it's kilograms?
This is math.
Okay? Can you show me mathematically how you get it?
Yeah. Do we have to?
You might.
Try to unit that.
So units, I got meters, and they're cubed, so meters cubed on top. They're divided by this Newton times meter squared all over kilogram squared times second squared, because this is where I get the second squared from.
What man, I'm trying to keep her from doing.
Bert, way to go.
You're good. So I'm going to go on and do this. I'm going to stretch this out and over. Life gets a lot better for me. Yeah. So I'm dividing by a fraction, which is the same thing as multiplying by the reciprocal. So I got meters cubed all over 1 times kilograms squared over newtons. Yeah. Newtons times meters squared times second squared. So,
Are we changing the newtons? We changing the newtons?
we are going to change the newtons. I'm going to cancel those meters squared out. Leave me with just meters there. Newtons. Newtons is equal to, so it's meters over 1 times kilograms squared over, the Newton is a kilogram times a meter over seconds squared. And this is times second squared. So now the second squared will cancel out. And then these meters will cancel. And one of the kilograms will cancel. Which will leave me with kilograms. Now this is the thing. This is not what the problem asked. On 44, it asks you for what is the mass of the star in the units of the sun's mass. You have it in kilograms. We have to get it into the units of the sun's mass. It's simple. It's easy. It's easier than what you want to think. I'm going to erase this. What's the mass of the sun, man? divided by the mass of the sun. And you'll find that it is 1.9241, the mass of the sun. Oh, Mr. Hall, that was so good. Questions?
I still don't get how you did the unit stuff.
Okay.
I wrote it down, but I just don't understand.
Okay, we'll go through it step by step. Are y'all good? Let's go for here. Like, are you good mathematically? Well, I did all that I've done here and over there to get the numbers that I got. We'll deal with the units here in like 2 seconds. So no questions mathematically on why I plugged where I plugged why I converted what I converted, nothing.
Go over how you flip the formula.
Here?
Yep.
Okay, so it's, what I did is I multiplied both sides by mass of the star. So it'll cancel mass of the star on this side and put mass of the star over here. We'll get mass of the star by itself. I'm multiplying the period times the mass of the star. So I divide everything by the period, which is why you see the period squared down here.
And you divide it by the sun's mass because at the end it said in units of the sun's mass.
Yes, it wants it in units of sun mass. So the sun, what I've done here is I literally use this one sun mass. Sun, not sun. One sun mass over the mass of the sun, which is 1.99 times 10 to the 30 kilograms. So it's kind of the same thing. Like we're saying sun mass here and over there. It's the same thing as saying this astronomical unit. So here, astronomical units, which is just the distance of the Earth to the sun.
So it's basically just conversion.
Yeah, it's all it is. So no questions with that, except for the units.
That's funny. What if they miss this? Oh.
All right. So I'm going to erase this and do the units, and I'm going to do the units slower. All right. Okay, so the units we got, I have meters cubed on top. Y'all see that? You got meters here and it's cubed, so meters times meters times meters. Now that's all divided by the Newton times meters squared all over kilograms squared times seconds squared. Good to where I got all that from. Alright. This is what I do. Because this is split right now, but it's just like a multiplication. That's all this is. So it's kind of like this second square has a 1 on it. I just put them together to where it'll be meters cubed all over newtons times meters squared times seconds squared, all divided by kilograms squared. Good to there? Now I've done this because now where I'm dividing by the fraction, it's the same as multiplying by the reciprocal. I have one fraction. So it's not like I have to figure out, like here I would have had to multiply by this, flipped it, and that second square would have stayed there. That's just confusing. Just flip the whole thing, put it all together. If you can put it together, put it together. So this is equal to meters cubed over 1 times the reciprocal of kilograms squared divided by newtons times a meter squared times seconds squared. Now I got these where they're just straight up fractions across from each other. So now things can cancel out a whole lot simpler and easier. So then what I do here is I'm going to convert that at Newton now. And this is why your units are so important. You know what you're dealing with, so you know what you need to convert. So this is equal to meters cubed over 1 times kilograms squared all over, what's a Newton? A kilogram times a meter over second squared times meter squared times second squared. And now I can start canceling things out. So the first thing I can cancel out are these seconds squared. Because it may be in a fraction, but there's a fraction there inside of that fraction. So the second squares cancel out. These meters squared will cancel out 2 of those meters cubed. So I have 1 meter left on top, but I got a meter left here on the bottom as well. So it'll cancel all the meters. So I'm left with kilograms squared on top and kilograms on the bottom. Kilograms cancel. It'll leave me with kilograms on top, which is the unit I was looking for. Because once I got into kilograms, then I can draw the relationship from the kilograms of that star and the kilogram of the mass of the sun. Feel better? That one you just got to do slow.
Your 2 is like a C.